Well, since Sanjay mentioned it, the first thing I'll say is SCOPE stands for Solar Connection Observatory for Planetary Environments. It's a proposed mission to study the way in which the sun interacts with different planetary environments and with the local galactic environment that is embedded in. And the idea behind that is that we study the Earth's interaction with the sun through the auroras and through the magnetospheric environment as the solar wind and solar radiation pressure affects the area immediately above the Earth's atmosphere and at the top of the Earth's atmosphere. It's very important to us, it's very important to satellites, what that condition is like. We have 8 other laboratories where we can study it, and one additional laboratory that's unique not only from body to body, but from day to day within the same body, and that object is a comet. Comets, as we'll get to by the end of this talk, I hope, you should get a sense that they're very dynamic objects, and they can serve very well as a probe of the conditions that they find themselves in. They're a very good barometer of their local environment. Behind here is a picture of a comet that many of you may have seen. It's Comet Hale-Bopp in 1997. That comet was visible in the skies on any clear night in April of 1997. You would have seen this comet if you looked for it. It's the brightest comet in modern times. So you were at least fortunate in that you were alive when that happened, and if you missed it, well, maybe in another 1,000 years another one like that will come. But it was a truly spectacular object. Okay, now my understanding is that you've been dealing with a lot of physics, the physics behind astronomy, the physics behind planets and the solar system and things like that. What I want to start off with is I wanted to say a little bit in that astronomy, like any other of the onomies, is really all about physics. It's about applying physical laws to the world that we live in. And astronomy just happens to be applying it to the grander universe that we find ourselves living inside. And astronomy provides us with a rather unique opportunity. It provides us with the ability to get beyond ourselves. Any laboratories that we deal with here are inevitably laboratories that are sitting in one gravity, in an atmosphere, within a very defined temperature range. We can't get too far out of those things. The environment that a comet is in, or any of the planets, if you go far enough away, is a vacuum greater than any vacuum we will ever be able to make on the surface of the Earth. And it's an expansive space that we can't possibly conceive of here on the Earth. And when you get to the time and distance scales that the universe describes for us, you begin to get the opportunity to look at a different kind of physics than we're able to look at just walking around and taking pictures of our local environment. Now, comets are very, very interesting as scientific objects in that they pull together all the elements of what science is all about. They are excellent fundamental laboratories. They are good for applied understanding of what physics is telling us about things. They are excellent in terms of being used as fundamental building blocks, giving us a sense of what the brick and mortar of planets and planetary systems is found. And they're also really fascinating social barometers. And I mentioned the last thing because something that you need to understand about science is that it is not all logic and facts. It's a human activity. It's something we do. It's clouded by our perceptions of what things are and how things are supposed to be. We try to divorce ourselves from that emotion and from ourselves, but we don't ever fully do it. And it does affect how our understanding of things changes with time. And it's true with comets. So I want to talk a little bit about that history and the sociology of comets. And then I'm going to branch off from there into their basic structure. What are they made of? What are the things that we call a comet? And then I want to talk about where they come from and what they really are. And then I want to talk a little bit about what they tell us about what the solar system is made of, where it came from, and where it's going. And finally, I'm going to bring it back a little bit to comets and their role in the modern solar system and where they are still changing the way things happen on the planets and even on the Earth. Okay. I may have already given you this idea, but comets are more important than you might think. They look very pretty in the sky. They're big, they're fluffy, they appear apparently out of nowhere. They do all sorts of interesting things. They change. They can be very bright. But they've played a critical role in our understanding of how the sun and planets are organized. Because comets that gave us our best look at how orbits that were non-circular come into play. It was comets that gave us our first really hard look at the very, very deep origins of the solar system. It is comets that provide the foundation, we find, on which planets are built. These are planet bricks. It's comets that also provide us with just a phenomenal astrophysical laboratory for studying gases, for studying chemistry, for studying plasma processes. All manner of physics occurs in comets in a laboratory we can never duplicate on the Earth. And comets have also played a significant role in the Earth itself, in the development of life on this planet over its history. It's possible there are theories that suggest that comets are the source of all the water on the Earth. Impacts with comets early in the solar system's history, providing us with all the water in the oceans, all the water that we're made of, in fact, all of the carbon, all of the nitrogen, all of the hydrogen, everything that makes us up, for the most part, may have come from comets and impacts with comets at some point in the past. And we as a species, and mammals in general, owe our dominance on the food chain and on the animal complexity chain, most likely to a comet that hit the Earth 65 million years ago and wiped out the dinosaurs. But for that event, mammals, which at that time occupied a very tiny niche of little shrew-like creatures, would probably still be in that tiny little niche of shrew-like creatures, and dinosaurs would continue to be walking around this area. So comets have played a very important role in the development of life on our planet, and will continue to do so in the future. And finally, comets have played an important role in the evolution of our species. That is, that they have been important throughout our history. When comets have appeared, people have made decisions based on comets. When comets have been in the sky, when scientists were looking at it at the right time, they were able to use their observations to learn more about the solar system, more about the universe, and expand our own view. So they've been a very, very important part of our exploration of the universe. Okay, so like I just said, comets have played an important role in human history. And this is a great picture of a comet over a temple in China somewhere around 2,000 years ago. And you can only imagine that if you're a Chinese astronomer and you have no idea what's going on anywhere in the universe, as far as you know, the Earth is all there is. You don't know that there's space. You don't know that the stars are suns like ours. You don't even know that the planets are other planets like the Earth. And then in the sky appears this bright, streaming object, seemingly at random. You can predict where the stars are going to be. You can predict the planets. You can't predict something like this. It just appears. So these objects really held a tremendous amount of fascination and outright dread for ancient civilizations. They were terrified of them. They were sure that they were always an omen for something bad. Part of the problem is that this is a kind of self-fulfilling prophecy. Because if you think about it in the news today, I mean, there's always news every night, right? I mean, they don't have the newscaster come on and say, nothing happened. Now, sports. I mean, you know, that never happens. So the point is there's always something happening somewhere, sometime, somehow. So a comet appears, somebody decides that comet's for them. Napoleon used a comet as his justification for why it was now time to invade Russia. There was a comet in the skies over London when the Black Plague was there. So they decided the comet was responsible for that. A comet had been ascribed from everything to the fact that Mount Vesuvius erupted and wiped out Pompeii. Heck, you know, there was a comet, or it appeared just before or just after, you name it. Superstition can allow you to tie things together in a very strange way. Now, we may even know today what comets are made of. We know their nature, we understand they're not related to the Black Plague or Mount Vesuvius, or they're certainly not telling Napoleon to invade Russia. But that doesn't change the fact that we still do crazy things in response to comets. In 1910, when Comet Halley came by, that was the last time before 1986 when it came by, they had just discovered that the tail of comets included a gas called cyanogen, which was presumed to be hydrogen cyanide derivative. And then scientists said, well, we're going to pass through the tail of Comet Halley. Well, this produced mass hysteria. People thought, well, we're going to pass through a cloud of cyanide gas, we're all going to die, human civilization's going to end. There were people out there selling pills and gas masks. There was a mass move to get people from the Western Hemisphere to China because it was thought that China would be on the backside going through the tail. So people behave strangely, even when they know the answers. And many of you may not know, but there was actually a mass suicide attached to Comet Hale-Bopp when it came by in 1997. A group of people had decided that this was a sign that they were going to be picked up by aliens and taken to someplace. I know. In any case, Hale-Bopp's on its way out. I hope they're with it. It's better than the alternative. But we haven't stopped having weird problems with comets. And in fact, you can probably think of what our current hysteria about comets is. It's sort of emblemized in films like Armageddon or Deep Impact. Now we sort of have this paranoid fear that one of them's going to come and smack us silly. And that's at least based in some sort of physics, but it's still, as we'll get to later, not real. Okay, so where do comets come from in terms of our view of the universe? Well, prior to the time of a great astronomer who you haven't talked about in this class, but I urge you to look up in the library because he's a very colorful character, a man named Tycho Brahe. He was a Dutch astronomer, lost his nose in a duel and replaced it with a silver one. A real interesting guy. Was probably the greatest observational astronomer that ever lived. And he lived back in the 1500s. And at that time, this was before Copernicus, before planets were anything other than objects on what they called the celestial sphere. They weren't separated from stars. Nobody really understood the way the universe was organized at this time. At that time, people believed that if it did not have a direct relationship to a star or a planet, it had to be in the Earth's atmosphere, because the heavens were by edict unchanging. They never change. And a comet broke that rule and hurt it. So they were thought to be clouds, and they look a little cloud-like. So early beliefs about comets were that they were atmospheric phenomena. Well, Tycho did an observation of it, and he attempted to identify how high in the atmosphere it was by using parallax. Now you know what parallax is, right? You covered it? Parallax is when I'm looking back at Sanjay, and I can draw an angle, and as I walk over here, that angle changes, and by measuring the change in that angle, I can tell how far away Sanjay is. Well, he did that measurement with the comet, and no matter where he went, it never changed. It was always the same. So he concluded it couldn't be part of the atmosphere. This was our first realization that the heavens did change. This was our first realization that objects moved across the sky unrelated to the stars and the planets on their own. Now, Tycho didn't buy the whole idea that Copernicus would come up with about the sun being the center of the solar system and the planets being like the Earth. And so he would never have believed the ultimate conclusion that we would reach later, which was that comets were like planets, just tiny. But what he did discover dwarfed our understanding of the universe. It made the universe a bigger place than it had ever been before. Now later on, another astronomer, Edmund Halley, and you can guess what he got named after him, noticed there was a comet in 1682. He looked back at the historical records and noticed that every 76 years there was a comet. And he speculated, well, if the planets orbit the sun, perhaps the comets do too. And this might be an object that would return over and over and over again. And he predicted that 76 years later, that comet would come back. Well, he died before the prophecy could come true, but in 1758, it did. And that became the first identification that comets were what we call periodic. They orbit the sun, just like the planets do. Okay, well, we know comets orbit the sun. We know that they are not part of the Earth's atmosphere. Aside from that, there are a number of very good reasons why we continue to study comets. The first reason, and probably the most important reason why we study them, is that they're time machines. The reason why is they're extremely old. They are the oldest things in the solar system. They have been unchanged, except in very, very minor ways, over the last 4.5 billion years. They are exactly as they were period of time when the sun became a star. Now when we look at the planets, when we look at the Earth is modified tremendously. The oldest rocks in the Earth, if we're very lucky, we may find 4 billion-year-old rocks, but most of the rocks in the Earth are less than half that age. And to get to those, you have to dig very deep. The Earth is a highly modified body. The same can be said at one level or another for all of the other planets, with the possible exception of Pluto, and I'll get to that. They've all been changed. They don't represent what was there at the beginning of the solar system. They represent what was left after the solar system formed, and they represent what has been changed since the solar system formed. So comets are very important in that they give us a chance to look back in time and see what things were a long time ago. And the nice thing about comets is, while there are objects like Pluto that I think could be equally primordial, comets save us the expense of having to go visit them by visiting us. So they come in very close and we get a good look at them. Now, as comets evaporate, the thing that makes them have tails and comas, they sort of spray off the material that they're made of. And we're able to look at that material and thereby figure out what comets are made of, what their density was, what their surface structure was, things like that. So that's how we were able to study them. And the second reason why we like to look at comets are that they're tremendous astrophysical laboratories, like I said before. The conditions that are found in the evaporated outflow of a comet are completely unique. A comet has an atmosphere. And you've been talking about atmospheres in this class. You've been talking about why the Earth doesn't have a hydrogen atmosphere. Well, a comet has a hydrogen atmosphere. It just doesn't have one for very long. Because it's melting, it continues to replenish everything that it loses. So it has an atmosphere that isn't what we would call steady state, but it is producing it all the time, all the same. And so we get to take a look at the process of how a gas evolves. Now, one of the things that people try to do in laboratories here is to take a gas and put it in a vacuum chamber and then shine light on it to break it down into its component atoms. But that's very difficult for certain types of molecular compounds because they react with themselves, they require very low density, they react with the interior of the vacuum chamber. They're very difficult, nasty chemicals to deal with. And some of them are downright poisonous, like hydrogen cyanide, things that you don't really want to mess around with to begin with. Well, all of these things are present in a comet. And so we were able to look at the distribution of these gases and how they change as a function of distance away from the nucleus of a comet. And from that, learn about the physics of what makes them the way they are and how the sun interacts with them. The other thing that we're able to look at is dust grains that are blown off the back of a comet. Comets are both dusty and gassy and icy. And those dust grains are, for us, a clue as to what the dust environment was like in the inner solar system or wherever they were formed at that time. And they're the only tangible way that we can look at what we believe to be dust that exists currently between stars in our own galaxy. Comets are somewhat representative of the local interstellar medium. And that allows us to take a look at that material and use it as kind of a proxy for those areas out there. And the other thing that comets tell us about is the sun. Because in addition to breaking down molecules, the sun and sunlight will also ionize them. They'll make them charged. And when they become charged, they interact with charged particles that are being thrown off the sun all the time, something we call the solar wind. And then when that happens, the charged particles are accelerated and dragged away by that solar wind. And if we know the properties of the comet component, it's a simple matter, well, not so simple, but relatively simple matter to develop a computer program that simulates the interaction between that and different configurations of the solar wind. So the comet becomes a windsock. It's like the windsock at an airport. It tells you what direction the wind is blowing, how hard it is blowing. If the wind slacks for a second and picks up again, you can see flaps in the windsock. Well, you can see that in a comet tail as well. Okay. Well, for everything that we want to look at with comets, what we're really getting at with them, the real core thing, is that they're cosmological objects. say that they're representative of the interstellar medium, when I say that they're primordial objects from the beginnings of the solar system. I'm really describing a fundamental body here. They are the outer solar system analog to the asteroids. The asteroid belt, those are rocky objects. We call them planetesimals. They formed in a process that's unlike the process that formed the Earth or Venus or Jupiter. They formed by grabbing material that was accumulated on dust grains in the early solar system, and they sort of rolled through the gas that was coalescing down to form the sun. And they began to get larger and larger, like a snowball rolling downhill. And those objects hit with each other, and they bound together. And when they bound together, they then hit with larger and progressively larger objects and formed, instead of planetesimals, protoplanets. Those merged together, and on and on and on and up to a hierarchy that ultimately produced Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. They are the building blocks that you make planets out of. Without comets, you have no planets. So we want to understand them, because if the planets are all formed out of this material, their current state today tells us what's happened between now and then to the material that's present there. Has it been differentiated, certain stuff at the top and different stuff at the bottom? Or is it the same as a comet? I'll tell you right now, Uranus and Neptune have a composition very similar to a comet. Jupiter does not. That's telling us something about the differences between the ways Uranus and Neptune formed and the way that Jupiter formed. And of course, the Earth, which has almost no water or volatiles compared to the amount of rock it has in it, is completely unlike a comet. That tells us, again, something about how the material has been modified. Okay, so if comets formed billions of years ago, they're building blocks of planets. And why are we seeing them today? Comets are basically snowballs. They're icy objects. Yet, whenever we see a comet in the sky, we are seeing a comet somewhere close to the orbit of the Earth around the sun. We know that that's not a good place for something composed of ice. And the evidence of that is that comets are melting all the time that they're in here. So they have to get here somehow, from somewhere. And the way they're getting here is effectively based on the laws of averages. How many comets are left from the formation of the solar system? Nobody knows the exact number, but it's probably somewhere in the neighborhood of hundreds of billions of these objects. And they occupy the extreme outer solar system. Now, even though there are hundreds of billions of them, the volume of space that we're talking about here is so unbelievably huge that these objects are tremendously separated. So they don't have very many opportunities to interact. But you have so many objects, occasionally two of them get together, and one will be thrown out of the solar system and one will be thrown into the solar system. And that's the reservoir from which we are getting all of the comets that we see today. Random interactions in the outer solar system. Now, there are people who talk about other things like nearby passes of stars, or some object that we can't see, a dim star or something, passing through this cloud of material that exists around our solar system and throwing in showers of comets. But we've never seen any evidence that that happens. And one other thing that I'm not going to mention this here as a source, because we have no proof that it's possible. But as I said at the beginning, comets are remnants of planetary formation. They aren't all from our solar system. If there are other planetary systems in the universe, and we now know for a fact that there are other planetary systems, they also would have gone through a phase similar to ours, in which comets were being formed into planets and thrown all over the universe. Some of the comets we see may not even be part of our solar system. We don't know enough about them to know whether that's true or not. Now, there are generally two reservoirs from which we get comets. The first is one called the Kuiper Belt. Now, the Kuiper Belt is a new discovery. This is kind of interesting. 10 years ago, nobody knew this was here. There had been a man, Gerald Kuiper, who had proposed it in the 1950s, but no one had seen it before. The Kuiper Belt is a vast reservoir of objects that exists in a range just beyond the orbit of Pluto, out to about 500 times the distance of the Earth from the Sun. That's 500 times 93 million miles. And what it is it's the leftover, what they call accretion disk of the solar system. It's the material that was being used to form planets. As you get farther and farther out in the solar system, there's less and less material. The areas are greater that you're dealing with. It's harder to form planets. And apparently at this point, there was not enough time or enough material to form a planet before the sun turned on and dissipated the remains of the material that was being used to form objects. So the Kuiper belt represents material that's frozen in time. It's representative of what the conditions were like at the time the solar system was forming in this area. That is, what was the temperature? What was the gas density? What were the dust grains like? That's frozen into these bodies. And we know exactly where they formed because they're more or less where they are today, the same as they were when they were formed. Some small perturbations, not a lot though. Now, in the Kuiper belt, one thing I want to point out, and this is the exciting thing about it from my end of things, is that the Kuiper belt isn't just occupied by small objects. There are big things there. There was a recent discovery, I think a few months ago, of an object 1,200 kilometers across out in the Kuiper belt. And there are estimates that there may be as many as 100,000 objects just past the orbit of Pluto with diameters more than 100 kilometers across. These are big objects. If they were anywhere else in the solar system, they have a name. As it is, they get numbers. But there's a huge number of them out there, and they range up in size possibly to include Pluto. And this is the big controversy that people have right now. Is Pluto really a planet? Pluto has a composition of a comet. It's just a really big one. So is it the planet that didn't get formed in that area and just a very big comet, or do we call it a planet in and of its own right? And it's a big argument that continues to go on in the field. Now, comets that come from the Kuiper belt tend to be confined to the inner solar system when they're deflected into it. They have shorter periods, and they don't go as far away from the sun when they go back. Comet Halley is a Kuiper belt comet. We call comets that have periods short enough for humans to recognize their distance, so that subsequent generations can record multiple appearances of the comet. Short period comets. The short can be 200 years, but short can also be 3.3 years. So there's a wide range of comets in this group. Now the second group where we get comets is from the Oort cloud. Now ironically, we discovered the Oort cloud first, or at least we theorized the Oort cloud first. The idea of the Oort cloud is that this was formed at the end of planet formation. And it's formed out of comets that existed in that swan of the solar system between Jupiter and Saturn. They're the material out of which Jupiter and Saturn originally formed. And when Jupiter and Saturn became very large gravitational objects, they began to prowl the outer solar system, effectively sending all the objects in that part of the solar system either into the sun, into their own atmospheres, or out of the solar system altogether. Now, a tiny fraction of those objects will get thrown into an orbit that is very, very distant from the sun, but not quite escaping. And that cloud of material out there was initially proposed by John Oort, is this Oort cloud. And it's huge, something like 1.6 light years across. It's just a mammoth area where these comets come from. And it's the same process. Very rare gravitational interactions will throw these comets into the inner solar system. Now what's interesting about it is that even though they're more distant objects, our understanding based on what I just said is likely that they formed 2 to 3 times closer to the sun than objects in the Kuiper belt. Temperatures were different there. So compositionally, they ought to be different objects than Kuiper belt comets or short period comets. Now, comets from the Oort cloud will have long periods. That is, very long periods, 8 to 10 to 20 to 100,000 years. Many times they'll come in on orbits that we call hyperbolic. They're not bound. They'll just leave when they're gone. They're done. We'll never see them again. So we didn't for a long time understand the difference between short and long period comets. This is something that's evolved only in the last few years. And based on what I just said about the fact that some comets, that these comets formed in different parts of the early solar system, suggests that we should be able to identify a physical difference between them. We haven't done that yet. We've identified some differences, but it's very difficult because short period comets tend to have been around in the inner solar system longer. So they've been affected by that, and that changes their characteristics. We have not learned enough yet to know the difference between the two. It's an ongoing central theme of cometary studies. Which time have I got left? 10 minutes? Okay. I'm gonna wing through this stuff because it's, what I'm gonna do is I'm gonna give you the web pages. I'll post them and give you the URL. You guys can all go and read these notes as you want. So anyway, I'm gonna just say just tell you quickly what a comet is made of. Comet nuclei, which is what is really a comet, is really a small object. The largest comet in modern times was Comet Hale-Bopp. We think that was probably about 20 to 40 kilometers across. Now that object would have been dimmer than the dimmest star you could see on any given night walking out into the country. But as a comet, Hale-Bopp was so bright you could see it standing in the middle of downtown Brooklyn. It's a great picture of that. I don't think you can say that about any other comet. So the thing that's actually the comet is the thing we see the least of when it comes by. So everything we know about cometary nuclei comes from material that comes off of it. Now only one time, and I actually have to update this, there's now been 2 times, but only one time in modern history until last December had we ever visited the nucleus of a comet, and that was when Halley came in 1986. There were 2 spacecraft, the Vega spacecraft and the Giotto spacecraft, both European missions, flew close to Comet Halley. And there's a nice picture of Comet Halley. And just last year, another satellite, the Deep Space One satellite, as sort of a finale to its mission, flew by Comet Borrelly and took a picture of Comet Borrelly. And I do have a picture of that later on. Sort of surprising, it looks an awful lot like Halley. We had no real reason to expect it to look like Halley, but there you have it. It does. It did. Now, what we have figured out from comets is that they're not spherical. Gravity has not formed these objects into a sphere because they're not gravitationally strong enough. And they're not uniformly active all over their surface. They're active in sectors, regions that are bright. There's a bright region on Halley. There's a bright region on Halley. And we probably know that the differences in the level of activity from comets, the amount of gas that they produce, is probably nothing more than differences in the size and the number of these active areas on the surface. And as they become choked off, something I'll mention in a minute, comet activity will go down. And so there are some comets that have been in the solar system a long time that are not very active, mostly because they've choked off most of the easily accessible active areas. Now, we still don't know what the interior of a comet is like. This is more of a planetary model where the densest material is falling to the center. We don't think that happened. This is more of an aggregate model. This could really probably describe a comet where different bodies have sort of moved themselves together. And the other possibility is that it's an undifferentiated single object. That is, it's just sort of the same material all over the world. Now, the consistency of a comet, at the surface anyway, is probably just as well expressed this way. It's more or less what dirty snow looks like in a parking lot at the end of the winter. That big pile that melts down at the bottom, it's kind of black and sooty and junk is in it. No candy wrappers, but everything else. And that's what a comet looks like. It's not pristine snowball. I know they show them on TV and in movies. They're always nice, white, snowy landscape. They're pretty ugly. They reflect less light than coal. Hard to imagine, isn't it? But that's true. What we see from a comet, though, are a number of very pretty little structures that are associated with these active sectors, general loss of material from the nucleus, and the interaction of that material with sunlight and the solar wind. The main structures are this coma, which is this bright circular thing that you see around comets and pictures, and then 2 tails, a dust tail, which is just dusty debris being swept back by sunlight shining on it, and an ion tail, which is this ionized material getting caught in the solar wind and dragged off. And then I drew in here some sort of active sectors. We call those jets. They'll produce characteristic patterns. I'll show you what that looks like in a few minutes. dust tends to be distributed along the orbit of a comet, is sort of left behind. The ion tail always points in the opposite direction toward the sun. So you could look at a comet and from the positions of its tails actually tell where it is. All right, coma of a comet is just the atmosphere. In the case of comet atmosphere, it's not bound, it just escapes. So it continues to expand outward as long as the material survives. Most of the gases that a comet is made of are destroyed by sunlight relatively quickly. Things like water is destroyed within 100,000 seconds. It's about a day. Other materials are destroyed in about that time frame. Water gets broken down ultimately into hydrogen and oxygen, both of which survive for very long times. So if you look at a comet in hydrogen, its coma can be tens of millions of kilometers across. Very, very large object. But if you look at it in water, which is where all that hydrogen is coming from, it's just a dot right in the middle. And by changing the color of the light, you can actually isolate specific compounds in the atmosphere of a comet. And I'll show you what I mean by some pictures I took of comet Hyakutake back in 1996. So this is a picture of comet Hyakutake using a imaging filter that isolated only dust from the nucleus of the comet. And this is a picture of Hyakutake that has both dust and cyanogen gas in it. And when I take the dust out of that picture, this is what Hyakutake looked like in cyanogen. And we identified back here this very, very interesting structure that turned out to be a gas interaction no one had ever seen in the tail of a comet before. But you had to look for it in the right species. So you look for different things in a comet and you can see different things. So when you say the coma of a comet, you've got to be very specific. Are you saying the hydrogen coma, the oxygen coma, the carbon coma, the cyanogen coma? It's different for different gases.